Ever wondered why some backend services handle thousands of requests smoothly while others struggle under load? A lot of it comes down to concurrency models. Let's break down how Node.js and Go tackle concurrency and what that means for performance. Node.js uses an event loop and async callbacks or promises, which makes it great for handling a bunch of I/O operations at the same time, like network requests, file reads, and database queries, without blocking the main thread. This means Node can juggle hundreds of tasks efficiently as results come in. What's the catch? If the main thread is stuck doing something heavy, like looping through a massive array or parsing a big JSON file, everything else has to wait. To work around this, Node can spin up worker processes using the cluster module or child process, letting us take advantage of multiple CPU cores. But that comes with extra complexity and some overhead for communication between processes. So bottom line, Node is great at handling lots of iOS operations concurrently, but it does not run JavaScript code in parallel by default. On the other hand, Go was designed with concurrency in mind. It uses Go routines, which the runtime spreads across CPU cores, allowing for true parallel execution on multi-core machines. If one Go routine is waiting on I/O, the others keep running on different threads. And if multiple Go routines are crunching CPU-heavy tasks, Go's scheduler automatically spreads the load across cores, making it scale really well. Go routines typically communicate through channels or other sync mechanisms, making it easy to avoid the usual headaches of manual thread management. Since Go can handle thousands of Go routines at once, it keeps things fast and responsive under heavy load, whereas in Node, some operations might get queued up. Let's quickly break down what CPU bound and IO bound mean. CPU bound basically means our processor is working at full capacity, doing heavy computations, things like crunching numbers, running complex algorithms, or rendering graphics. If our program is running slow, it's because the CPU is maxed out. In this case, upgrading to a faster processor or optimizing our code would make a big difference. IO bound, on the other hand, means a program spends more time waiting for data to load from a hard drive, waiting for a response from the internet, or waiting on a database query. The CPU isn't really the problem here. It's just sitting idle while these operations finish. So instead of upgrading the processor, we would see more improvement by using faster storage, a better network, or optimizing how data is fetched. That's the theory, but to really see how these differences play out, let's dive into an example. So in this file, I've got two async functions. Fetch data, which fetches data from a given URL, which is right here. And all it does is it makes a HTTP request, and then in this line, turns response into a usable JavaScript object. And finally, it returns the data. Here in this functional run, this is where things get interesting. It starts a timer to measure execution time. Then it calls fetch data twice using promise all. This means both requests happen at the same time instead of waiting for one to finish before starting the next. Once both requests complete, it logs right here. It logs the data. Finally, in this line, it stops the timer and shows how long everything took. So it's pretty straightforward. Let's run this code to see how long it takes. It took 246 milliseconds. I'll run it multiple times, 239, 265, 242. So by average, we can see it's around like 250 milliseconds. In this file on the right-hand side, I have the exact same code. I mean, exact same functionality, but written in Golang. I have a fetch data function here. Here, again, I have a timer. I start a timer. Then at the end, I just log how long it took to execute the whole thing. And I got two Go routines here. Let's now run this to see how long it takes. 243 milliseconds time, 231, 138. So it looks like the average is almost like around the same number that what Node had. So now what's important to notice here is this is an IO bound operation. Like I mentioned a few minutes before, this is because we are waiting on an external resource to receive data from them. Same thing here. This is IO bound. So let's see what happens if I change this IO bound to a CPU bound. I already wrote a function here. All it does is computes a Fibonacci number for us. And I'm going to call it here instead of fetch data. Let's say 45, 46. I'm going to do the same thing here. We're passing 45, 45, 46. Is that? Oh. Saved. All right, now let's run both. We see now because we have CPU bound in both languages or both files, let's see what's going to be the result. Probably it's going to take a few seconds or maybe a bit more. Okay. It took for Golang to compute this almost 8 seconds. Let's see how long it takes for Node. 22 seconds. By doing a really simple comparison, we can see what a big difference changing IO bound to CPU bound makes in Node versus Golang. So for IO bound tasks, both Node and Go perform very well, as we saw. And usually the differences are negligible. Node's non-blocking IO model is extremely efficient for tasks like serving files or proxy requests, and Go's network libraries are highly optimized as well. So when does performance actually differ? If our backend is mostly handling API requests or serving static files or acting as a proxy, Node.js really shines. But if our app involves heavy data processing like video encoding, real-time analytics, or machine learning, Go's ability to efficiently use multiple cores makes it the better choice. In short, Go scales up better under heavy CPU-bound workloads, while Node is fantastic for async IO-heavy applications.